This is Unit 1.2, Laws of Logic in Symbolic Notation. There's going to be a lot of writing on these slides, so feel free to pause or to go back and look at this anytime. But let's look at symbolic notation. So we've talked about conditional statements already, and we said that they contain two parts, a hypothesis and a conclusion. So for example, if you have the statement, if x equals 5, then 2x equals 10, that's a conditional statement. So symbolically, so using symbols, we can write that statement by using if P then Q, or P and then an arrow to the letter Q, where P always represents the hypothesis and Q always represents the conclusion. Now, I didn't just make this up. This is a language that all mathematicians use when they're talking symbolically about conditional statements. We can also write the converse of a conditional statement using these symbols. So again, if we go back to our original, on the last slide, we said if x equals 5, then 2x equals 10. So that's our original conditional statement. So we know the converse is, and we've learned this already, that the converse, we would say if 2x equals 10, then x equals 5. So when we write this symbolically, we're going to say if Q then P, or we could use the arrow Q to P. So if Q then P. Now again, P still represents the hypothesis. Q represents the conclusion, and we're talking about the original hypothesis and conclusion. So from your original statement. Now let's look at it using our biconditional. So just to review, we said we can only write a biconditional when both the conditional statement and the converse of the conditional statement are both true. So going back to original, if x equals 5, then 2x equals 10. So the biconditional we can write symbolically with a two-way arrow. So before on the last slide, the arrow just went from left to right. This is a two-way arrow. And if I read this, this is going to read P if and only if Q. So when you look at these arrows, you literally read if and only if. Or we could write the biconditional the other way, Q if and only if P. So again, P is always going to be that original hypothesis and Q the original conclusion. All right, now in your notes, you are going to try to write down some of these examples. So you're going to use these statements. You're given P, that it's raining, Q, that it's warmer than 32 degrees, and then you're given R. So really all you have to do is look at the arrow in these statements 1, 2, 3, and 4 and think, is this an if-then conditional statement, or is this an if and only if statement? So in your notes, I want you to try these on your own first. So you're going to need to stop the video, write them down, and then you can check them on the next slide. Hopefully you were able to pause the video. Let's check these. So if P then Q. So if it is raining, then it is warmer than 32 degrees. If R then Q is number 2. So if football will practice, then it is warmer than 32 degrees. Then when we look at our last two, these are our biconditionals. So R if and only if P. So again, we read our R statement, football will practice, if and only if it is raining. So maybe these aren't true statements. That doesn't make a lot of sense, but that's how we would write this. And then lastly, Q if and only if R. It is warmer than 32 degrees, if and only if football will practice. So again, we're just practicing writing those statements. All right, this next slide is really, really, really important. And what's important is that not so much that you remember what this is called, but that you understand the concept of the law of detachment. So the big idea is that if a conditional statement is true and the hypothesis occurs, the conclusion must occur. So that's like a much easier way of saying all this stuff down here. So you can read this if P then Q is a true conditional statement and P is true, then Q is true. But the idea is if the hypothesis is true, the conclusion must be true for the conditional statement to be true. So if we look at this example, if two angles are vertical angles, then they are congruent. So if you have two angles that are vertical angles, they must be congruent. So if I tell you that angles 1 and 2 are vertical angles, and we've told you that this is a true statement here, then we can conclude that angles 1 and 2 are congruent. So here's where it gets tricky. Let's think about this. So again, we said if the hypothesis P is true, then Q must be true. But it doesn't go the other way. So if Q is true, fine, but it doesn't mean that P is also true. So the hypothesis proves the conclusion, not the other way around. So if two angles are vertical angles, then they are congruent. That's our original statement from the last slide. So then if I tell you that angles 1 and 2 are congruent, can we prove that they're vertical angles? And if you just think about the law of detachment for a second, no, that's not enough information. I'm sure you could think of other types of angles that are congruent and that aren't vertical angles. So this is an example where we're given the conditional statement, it's a true statement, and then we're told the conclusion's true. But we don't know that those angles are vertical angles. So let's use our knowledge, our developing knowledge of this law of detachment, this idea that if the hypothesis is true, the conclusion must be true. But the conclusion could be true and the hypothesis may or may not be true. So what I want you to do is decide if you think this reasoning is valid or invalid based on that. So Donnie knows that if he misses practice the day before a game, then he will not be a starting player. So Donnie misses practice Thursday. So he concludes that he will not start on Friday. Think about that. Is that valid or invalid? All right. So again, we are told the hypothesis is that if he misses practice, that's like our hypothesis. And the conclusion is that then he will not be a starting player. And then we're told that the hypothesis is true. So it is totally valid for Donnie to conclude that the conclusion will also be true. Let's look at a second example like that. So again, same idea. So our statement is that if two angles form a linear pair, then they are supplementary. So again, our hypothesis, two angles form a linear pair. Our conclusion, they are supplementary. So then we're told that A and B, should really be angles A and B, huh? Angles A and B are supplementary. So someone concludes that A and B form a linear pair. Do you think that's valid or invalid? Well, let's go back and look again. We said our hypothesis must be true, then the conclusion's true. What we're told here is not that our hypothesis is true, but we're told that our conclusion is true when we're told that A and B are supplementary. So that's fine, but the conclusion does not prove the hypothesis. So this is actually invalid reasoning. You can't conclude that they make a linear pair just because they're supplementary. They could be supplementary but non-adjacent. And those types of angles are supplementary but not a linear pair. All right, we've got one more law of deductive reasoning to talk about, and this one's called the Law of Syllogism. And again, it's much more important to me that you really just understand the idea behind it than remember that that's what it's called. So in this law, it says that if two conditional statements are true and the conclusion of the first is the hypothesis of the second, then if the hypothesis of the first is true, the conclusion of the second must also be true. Whew, it's a lot of words. You can also read this part right here if you'd like. I'm going to skip down. I think you'll understand this from going over the examples. So if we look down here, oops, where's my pointer? Here we go. If P then Q, then we have if Q then R, and then we're going to be told some things about this. So here are two statements. If I am hungry, then I go to the kitchen. My next statement is, if I go to the kitchen, then I eat a snack. So if this next thing is true, this hypothesis, P, I am hungry, we can conclude from that I eat a snack. So not only could I conclude that I go to the kitchen, but I could then jump to this next statement and conclude that I eat a snack. This law reminds me of like a domino effect. If you've ever set up a bunch of dominoes, like and then knocked one over, it knocks down all the other dominoes. So I like to think of these when the statement shares, when one conclusion is the hypothesis of the next, we can kind of think of it as like this domino effect, that if this is true, then this must be true, therefore this is true, therefore this must be true. We're almost done with this. We just need to practice this a little. So if you read this, I want you to try to draw conclusions from these two different pieces of information down here. So treat them like two separate examples. So the first is that, and we're told the statements are true. If you liked the movie, then you saw a good movie. If you saw a good movie, then you enjoyed yourself. So we're going to say that you liked the movie. What must be true? And the second example is, if you vacation at the beach, then you must like the ocean. If you like the ocean, then you'll like Florida. So we're going to assume that it's true that you vacation at the beach. So what is the most final thing you can conclude? What must be true about that? Go ahead and stop the video. Jot these down in your notes. Try it and then restart, and we'll go over the answer. All right, so what we can conclude in those two examples is two things, one for each. So in the top one, I told you that you liked the movie. So we could conclude that you enjoyed yourself. And if you just wrote you enjoyed yourself, that's fine. The second one, we said that that it's going to be true that you vacation at the beach. So if you vacation at the beach, then you'll like Florida. So if you just wrote you will like Florida, that's really also what I'm looking for here. All right, I know this is kind of a long video, but it's so important that we practice this. So just one last example. This is a longer law of syllogism problem, and these aren't always in order, so the order here matters. So the following statements are all true. If John goes out, then he needs money. If John takes money from his mother's purse, she gets angry. If it's Friday night, then John goes out. And if John needs money, then he takes it from his mother's purse. So we are told that it's Friday night. What can we conclude? I'm going to model for you how I would do this if I were the one solving this. So we know it's Friday night. That's true. You want to look through these statements and you want to look for a hypothesis that says it's Friday night. Don't look at the conclusions. So we see a hypothesis. Excuse me, we see a hypothesis in the third statement that says that it's Friday night. So, it's Friday night. So that statement is true. So if it's Friday night, then we know John goes out. This part has to also be true, because if the hypothesis is true, the conclusion must be true. All right. So then we look for another one that, we look for another statement that has that as its hypothesis. And you see it in the top. So now we see if, thought that was a highlighter. If John goes out. And again, that's matching John going out. So if John goes out, then he needs money. So, he needs money. And I thought that was not a highlighter. So we know John needs money. So now we're looking for a statement that starts with John needing money. And we see if John needs money, then he takes it from his mother's purse. All right. John's kind of a jerk, isn't he? So if he takes it from his mother's purse is our conclusion. But then we link back to this statement. If he takes it from his mother's purse, then she gets angry. So this thing that's left, this is like the most final thing that we could conclude is that she gets angry. So if we look, we don't know that John is at a football game. We don't know anything about him borrowing money. We definitely know his mom's angry. We don't know that his dad grounds him for it, though. So the only thing we can conclude from these logical statements is that John's mother is angry.